If S is a piecewise smooth surface, that is to say, it consists of multiple surfaces SI that intersect only on their boundaries, then the surface integral over S of f of x, y, z ds is equal to the sum of the surface integrals over the surfaces, say S1, S2, dot, 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 S sub n. Kind of like a line integral when C is given to be multiple curves. This will be useful in our next example. Evaluate the surface integral. The surface integral over S of x squared plus y squared plus z squared ds, where S is the portion of the cylinder x squared plus y squared equals 9 between the plane z equals 0 and z equals 2. Now that itself would just be one surface. But then we have together with its top and bottom discs. As soon as we have the cylinder together with its top and bottom discs, now we have multiple surfaces. Let's see what this looks like. So here we have a base disc in the xy plane. We have a top disc at a level of z equals 2, and then we have the cylinder itself. Let's call the cylinder S1, surface 1. We'll call the top disc surface 2, and the bottom disc surface 3. And as with a line integral with multiple, I forgot a parenthesis there. As with a line integral with multiple surfaces, we have to handle each of these in its own turn. So for S1, which is the cylinder, it's a cylinder of fixed radius, right? It's a cylinder of radius 3. And so x is going to equal 3 times the cosine of theta, y equals 3 times the sine of theta, and z equals z. We are allowed at most 2 parametric variables, and we have here theta and z, so we're doing all right. I'm actually going to point out additionally, I've already said it, but the cylinder has a fixed radius. Our theta cross our z is going to equal negative 3 times the sine of theta, 3 times the cosine theta, 0 across, I almost wrote dot, cross 0, 0, 1. And you can verify that the magnitude of r theta cross r z is equal to 3. So the surface integral over the surface S1 of x squared plus y squared plus z squared, remember the parenthesis that time, dA, is equal to, let's go back. Now, for the cylinder, z goes from 0 to 2, and theta goes from 0 to 2 pi. So our integral is the integral from 0 to 2 pi of the integral from 0 to 2 of x squared plus y squared plus z squared. Well, x squared plus y squared is equal to 9. So we have plus z squared. For dA, we have 3 dz d theta. You can confirm this evaluates to 124 pi. Now let's turn our attention to S2. S2 is the top disk. Now folks, there's a difference between this top disk, which has an interior, and the cylinder, which didn't. The cylinder had a radius 3. It was fixed radius. We used 3 cosine theta for x and 3 sine theta for y. When we think about a disk, we think back to what we've done in previous sections where D is the projection of D is a circle in the xy plane with its interior. So when we consider S2, which is again the top disk, we're going to let x equal r times the cosine of theta, y equal r times the sine of theta, and z is equal to 2 because that disk has a fixed height. Let's note that r is going to go from 0 to 3 because it's a disk of radius 3. I almost said circle. It's a disk. It contains its interior. And theta is going to go from 0 to 2 pi. That's going to help us set up our integral. Notice we didn't use a variable for z. We used them all up. R and theta, we had no more variables left for z. So it had to be expressed in terms only of a constant or in some cases, depending on what we're looking at, in terms of the parameters, which are r and theta in this case. So r as a function of, well, we kind of have a weird thing going on here, right? R as a function of r and theta, and we know the difference because r the function is a vector and r the not function is not a vector, is equal to r times the cosine of theta, r times the sine of theta, 2. And so the partial of r with respect to r is equal to the cosine of theta, sine of theta, 0. The partial of r with respect to theta is equal to negative r times the sine of theta, r times the cosine of theta, 0. You will find that the partial of r with respect to r cross the partial of r with respect to theta is going to turn out to be r, the parameter. For the surface integral, then, we have the surface integral over S2 of x squared plus y squared plus z squared dA is equal to the integral from, and we said theta was going to go from 0 to 2 pi, r is going to go from 0 to 3, and then x squared plus y squared is equal to r squared. Z is equal to 2, so z squared is 4. So we have r squared plus 4, and then r dr d theta. Wait a minute, why r dr d theta? We were in r and theta to begin with. Folks, this r in r dr d theta came from the cross product. The result here, I'm sure you will confirm, is 153 over 2 times pi. Now, if you thought all that went fast, wait till you see what we do with S3. S3 is the bottom disk. It's still radius 3 and has a z-value of 0. So we're actually going to cut right to the chase here. For S3, which is the bottom disk, our r as a function of r and theta is kind of like what we just wrote. R cosine theta, r sine theta, 0. The magnitude of r, the partial of r with respect to r cross the partial of r with respect to theta is again going to be r. And so our surface integral over S3 of x squared plus y squared plus z squared dA is going to equal the integral from 0 to 2 pi of the integral from 0 to 3, that's the disk, times r squared plus 0. You see here, z is 0 for the bottom disk, r dr d theta. Result there is 81 over 2 times pi. Now we can put it all together. The surface integral over S of x squared plus y squared plus z squared dA is going to equal 124 pi from the cylinder plus 153 over 2 pi from the top disk. That's 153 over 2 times pi, right? Not 2 pi in the denominator. Anyway, plus 81 over 2 times pi from the bottom disk. In all, we get 241 pi as our surface integral.